basically you can factor out r to the delta plus m, and then get a bunch of other stuff, which I won't write down. So the reason why you get this r to the delta plus m is that when you're going to the cylinder, basically, remember you take an operator on the flat space, and it equals a cylinder operator, basically up to this factor of r times whatever the scaling dimension is. And so that's why you get an r to the delta plus m, because you had basically an operator delta plus m here. And so the reason why I'm saying this is just to say that when you write this conformal block as a sum of operators, it is a natural expansion in r, which is the radial direction. And r can be related to u and v. So in particular, we can write down this diagram like so. So this is a radial diagram. So let's make x1 be here, x2 be here. This is the origin. Let's put x4 here. We're putting these points here using conformal transformations. So that's the idea. So we're using translations, rotations, dilations, and inversions to put these points like this. So that means x4 and x3 are totally fixed. So x4 is just -1, x3 is 1, and then x1 and x2 are fixed at this kind of arbitrary thing, rho. This is minus rho, and this is rho. And then when you use, so this is basically you're fixing the conformal frame. This is related to the fact that in a 4-point function, there should just be 2 variables, whereas you started off with, 4 times d, because you had 4 points at arbitrary things. And so after fixing this, you'll see that you define these variables. Rho, in terms of the variable z, is 1 plus square root 1 minus z squared. And then rho bar is just putting bars here. And then r equals basically the magnitude of rho. So it equals the square root of rho over r. And so that's how you define r. And then you can also define eta similarly as basically the angle between these guys. Definition of eta. Well, eta is basically the angle between rho. So, should have put better definitions in there. Let me get back. I can't find it anymore. Let me get back right there. Okay, so the point of this is just to say it's a natural expansion of this variable r, which can be related to the variables u and v, using this chain of definitions from r to rho, from rho to z, and then from z and z bar to u and v. And so now the way this homological recursion works is that we write the conformal block in terms of these r and eta variables. So first of all, we take off the value when scaling dimension is infinity, which is going to be a certain entire function of r. So and then it's going to be a sum, and I'm going to explain the sum in a moment. So sum over I, sum over n, bi, cim over delta minus delta im of another conformal block at delta im plus m l im. This thing is also just a function of rn. So the reason why you have this formula is basically we start with the observation that if you take an operator O delta L, and if you allow the scaling dimension delta to be below the unitarity bound, then there exists a certain descendant, P, an nth level descendant, acting on our primary O delta L, so this is going to become null. So basically this thing becomes 0. And this only happens for when delta is less than unitary. So this is not a physical value of delta, because remember, all physical values of delta have to be bigger than these bounds, but just if you analytically continue, you'll find that this thing becomes null. And this is the case when M is in a certain set, which we call BI, and then I, there's like 3 families of these sets. So basically, there's certain special descendants for non-unitary values of delta, where the operator becomes null.
Sorry, Shai.
Yes.
No, you mean norm is equal to 0, not that it's self equal to 0.
Sorry.
I mean, that distinction is actually quite important.
Yeah.
Since we're talking about non-unitary variables.
Yeah, sorry. So the idea is that it's norm equals 0. And so because you have these null states, that means you know that the conformal block has to have poles at these values. Because this is another way of saying that the state is becoming 0. So that's what motivates this ansatz, that the conformal block has to equal a sum of conformal blocks at these weird non-unitary values of delta, as well as the associated spin, where there will be these poles. So that's what motivates this formula. Then the way we fix the various parts of this formula, so this guy, we can fix this by looking at the delta goes to infinity limit of, and in that case, based on what we learned here, the things in general scale like r to the delta plus m, we know that this block has an essential singularity as delta goes to infinity of 4r to the delta. And that motivates us to define some auxiliary quantity we call h delta L of r and eta, where we just strip off this essential singularity from the block. And so then if we rewrite this recursion relation in terms of h, this is just going to introduce factors of r here. So that means in terms of h, let's put an h there and an h here, you're going to have some h infinity, which will be some function of r, some entire function. And then here, you're going to have something which is naturally an expansion in 4r to the n. And so this is now a good recursion relation in terms of r. Because the idea is that you could start at the lowest level where you just have h infinity. This you can solve from the Casimir equation, just by looking at that limit. Because in this simple limit of delta goes to infinity, you can actually just solve the recursion relation in general. And so you start with this input for any d. And then you just start running this recursion relation order by order in R, using these coefficients C, which are fixed by conformal kinematics. I give the explicit formulas in the lecture notes. They're rather hideous. And this will just build up this h function order by order in R. And then at the end of the day, when you want to get back to the block, you just multiply it by 4r to the delta, and you're done. And so at the end of the day, the structure of a block, which you will get from this recursion relation, is that a block, delta L, in terms of r and eta, it's going to be some expansion in r, so say like 1 times something plus r squared times something, etc. And then each of these somethings is going to include poles at various values. So some value I, this will include poles at some other value, say like delta I prime, etc., where these poles exactly correspond to these null descendants. And you're going to have more and more poles as you go to higher order in R, but there will always be a finite number of terms here. And then the other dependence on delta just comes from this overall factor of 4r to the delta. So the dependence on delta in this homological recursion relation is very simple. So you have this exponential dependence multiplying everything, and then you have simple meromorphic dependence on delta, order by order in R. And so it's this specific dependence on delta which will actually be very important in certain formulations of the Bootstrap algorithm. And so it's important to keep in mind that the conformal block has this simple delta dependence, order by order in R. You also have functions of eta that show up at each order, which are also just fixed kinematic. Okay, so I've kind of sketched out how the homological recursion relation works. In order to get familiar with it, though, you really should look at the problem sets in the lecture notes, which I will email out, which give kind of practical demonstrations. I give example answers, so you can do the calculation yourself, check to get the right answer. Once you know how the conformal block recursion relation works, though, I can just reveal to you that there's also a software online which just computes it to you to any order. And so for practical Bootstrap applications, you won't have to go through this tedious exercise. Thankfully, people have done it for you. And in coming lectures, you will actually use this online software. So, just to give an overarching description. So the 2 lectures we've done have been the analytic, you say conceptual introduction. In the 3rd lecture, which will be next week on Friday, we're going to give the first practical demonstration of using the Bootstrap. So we're going to talk about Bootstrap algorithms, how to implement them using these blocks, which we just discussed today, as well as unitarity and other important aspects. And then we're going to compute our forced Bootstrap bound. And in the accompanying lecture notes, I'm going to lead you exactly how to do that using freely available software. So keep tuned for next week. That's it.
I just want to elaborate more on the intuition for the recursion. I think that you only explained half of it. So when you continue the whole block in delta to a regime where you divide the unitary bound, you find a null state, that from this formula here, because you're dividing by the normal null state, is obvious that the whole block is expected to diverge, so expect a pole. But that's only a part of the recursion relation. The recursion also says that the residue at the pole is proportional to another conformal block where the delta is shifted. So the reason for that is because the null state itself behaves like a new primary. It allows yourself to consider non-unitary theories, and it generates its own. The descending is further from null state in its own conformal family.
Yeah.
And the conformal block is now dominated by this new conformal family, which starts at the descendant, and that's why you get something proportional to the new block.
Yeah. That's another important thing to mention. Yeah. And this is specifically because you have this zero.
You said Friday next week?
Yeah, so next week it's at an unusual time. It's not Wednesday, it's Friday.
And also it's in a different location. It's the Science Center D.
Yeah.
Center D.
Yeah, so this will be reminded in the emails.
Just for next week, right?
Yeah. And then there's going to be a break for roughly a month. But that break comes at a good time, because during that break you guys will have ample time to actually do the problem sets and compute your first Bootstrap bound, which you will be able to do after next lecture. And then the 3 lectures after the break are going to be on more advanced topics, stuff like global symmetries, other fancy methods you can use to make the Bootstrap better, and then eventually I'll just give kind of like a status of the Bootstrap, open questions, etc. The idea is that these first 3 lectures, by the conclusion of them, you should be able to do basic Bootstrap problems yourself. And then you'll be able to do that during the month break. So any other questions? I mean, you guys don't have to say, but.